Okay, go for it.
Okay, so I'm going to give a little intro to Julia here, and I struggled a bit with how exactly to organize this. I spent like way more time than I usually do giving a talk as short as this. Greg had suggested I just kind of walk you through how to do some image transformations, and that completely makes sense given that so many people do that kind of thing here. But to me, the main kind of differentiator of Julia is that it solves what's called the two-language problem. And so I kind of wanted to kind of highlight that here because I think that is its main reason for being. So let me share my screen here. Okay, are you guys seeing this Nature article called Julia, Come for the Syntax, Stay for the Speed?
We
Okay, chose the right one, yeah. So the idea is that researchers, and I'll just read this, often find themselves coding algorithms in one programming language, typically a high-level language like, pick your favorite one, MATLAB, Python, or whatever, only to have to rewrite them into a faster one, typically C or Fortran back in the old days or whatever. And so the whole idea was that Julia, you don't need to do that. It provides a very seamless workflow towards optimizing your code to be as fast as the low-level languages that are typically used in high-performance computing on the big national lab clusters type of stuff, right? So I'm going to kind of get to the command line script and kind of show you kind of a specific example of how to do that. Before we get there, I just wanted to show you how you can install it if you haven't played around with Julia already. If you're used to Conda, Mark Kitasopical, who's here, right, nicely created a recipe, is that what they're called, for Conda to install it. So that's kind of an easy way to install it. If you've got a Mac and you want to install it on your Mac, it's got a homebrew recipe, so you can use that. Alternatively, what I just do is I just go to julialang.org and I go straight to the downloads page, and you can kind of click on these and download them for any kind of the supported platforms. Once you download it, there's a variety of code editors that are supported. VS Code, Visual Studio, right, is I think a really popular IDE, right? And Julia has full support in there. Alternatively, if you like Jupyter Notebooks, either for for all your work or just kind of hashing out a little example or whatever, the JU in Jupyter stands for Julia, and so of course it has support there too. But typically what I do is I just use the REPL, as it's called, the read evaluation print loop on the command line. And so this is here my terminal on my workstation in Linux, right? And I'm just starting Julia here with the -T flag to spool up threads so that it's multi-threaded. Version 1.7 is the latest version, just came out a couple months ago. And what I'm going to do here is I kind of picked a pedagogical example, which is purely pedagogical. You would never actually choose to do this. But the idea being that just to kind of illustrate how you can write your own code to be just as fast as built-in functions. So everybody who's ever coded in MATLAB or Python knows that you need to vectorize things, right? So if you have some big array or whatever, and you want to compute some function on it, you have to go find the built-in function that language provides to do it, or otherwise it's going to be insanely slow. And so what I want to kind of show you today is that that's not the case in Julia. You can actually write your own for loops, as I have here, and they are largely just as fast as if you use the built-in function. All right, so I've chosen to use the dot product, right? Just because there is a built-in function for that. And I'm going to rewrite that in Julia. This is how you'd rewrite that. Just a for loop over each index in the vectors, and you accumulate the product of the two vectors in an accumulator function, accumulator value, and you return that, right? So if you time this, and so we can go ahead and then make sure that my code is the same with this approximately equals operator, that dot, the built-in function, matches my dot, which is my kind of homebrew custom rolled dot product operator. And then using a package called benchmark tools, which kind of it nicely takes care of all the little details you have to think about to do benchmarking without any kind of things getting in the way of an accurate measurement. You can just time them and you can see that you're within a factor of 8 here. Now, you say, Ben, hold on, you said you can get very close, factor of 8. It's not anywhere close. So what's going on here is that BLAS, this dot function, actually calls out, the built-in function calls out the BLAS. And the BLAS default for the number of threads is however many cores your machines have. So if you actually then go back and set it back to 1 and redo the timing without BLAS being threaded, you can see now that we're within a factor of 2. Our hand-rolled loop here, right, is within a factor of 2, 900 microseconds versus 500. Now, okay, what about the flip side? How can you thread your hand-rolled function to be as fast as the BLAS function? All right, so we're going to create a new function here where we hand roll our loop and call it threads underscore dot. And really all you have to do is prepend your for loop, right, with threads dot at threads. And what that does is it takes the iterations through the for loop and it partitions them into folds. In this case, 8 folds because we have an 8-core machine, right? And it takes each fold and sends it off to a different thread, and then the block within the for loop executes on those threads separately. And so, of course, then you have to have your accumulator has to have you have to have a separate accumulator for each of those threads. And so it's a little more complicated here, and you have to do a sum at the end. But in the end, you can test to make sure that my little code here worked right, and then you can time it, and you can see we're back down to 181 microseconds compared to 149. So we're, what is this? We're maybe only 20% slower here, something like this, right? And this is for a hand-rolled for loop, right, in the native language, right? And it's very comparable to what you get with a built-in function. And not just a built-in function, but a built-in function which is calling a BLAS library written in C, right? That's how fast the for loops are in Julia. So another way to do this is with an external package called loop factorization, which a guy working at a pharmaceutical company kind of wrote in his spare time. So this kind of nicely provides kind of some sugar, syntactic sugar. So you don't have to say at threads and then have the special accumulator function and everything like that. And on top of that, it also uses AVX or any other kind of like CPU-based single instruction, multiple data type of vectorization that your hardware is capable of. And here, all you have to do is say at turbo threads equals true, right? And then everything else is exactly the same. Actually, that's not true. I've also added an at inbounds here to where Julia will no longer check to make sure that your index I is within the bounds of this variable. If when you're first writing your code, you don't put this in there, but after you've got all your system tests and everything to make sure that it's right, then you can put that in there and you can avoid another kind of if statement to check that everything's within bounds. Once you do that, then again, you can kind of test to make sure that you wrote your code properly, that it matches the built-in function, and then you can time your this new function, and we're down to 161 microseconds. And again, that's compared to, where was it, 149, right? So within 10% this time, right? Even 5%, right? You can get. So to me, this then solves the two-language problem. There's no reason to write something in some high-level languages to prototype and work out the math and kind of the global algorithm that you're doing. It only then to have to rewrite it. If you want to scale up really big, you can just write it in Julia, and then it's just as fast as if you would otherwise. So kind of to drill home this point, I guess I still have like at least 5 or maybe 10 minutes, right, Greg? So I'm going to finish way early. I've only got like 2 or 3 minutes more worth of stuff I'm going to say.
That's totally fine, because I'm going to assume there's going to be a question or two. I'll have a few, so we can use some of that time for that too.
If you have questions already, please jump in.
I'll wait till you finish for mine, but if there are other questions, go for it.
I have a quick question about this inbounds thing.
Sure.
So I'm just curious about that. Like, what's the reasoning behind putting this as an annotation in the code instead of like disabling it for the entire program when you're kind of running in a production?
I think it's, well, I mean, you could imagine doing that. You can actually put the inbounds up here, right in front of the function. And it would disable it for everything within inside that function. I don't think you can take it any higher. Maybe Mark would know that. Can you add inbounds a module, for example, Mark? I'm not really sure. But I think
no.
Yeah.
But you can disable it for everything. There is a check inbounds option to the Julia executive. So you could say dash a check bounds yes or no. That will technically disable it everywhere.
Oh, so on the Julia command line, you're saying?
Yeah.
So there's a check inbound somewhere here.
Yeah. Right above math mode there.
Okay.
2 lines up. Yeah.
What happens when you
Oh, here it is.
disable it and you actually have a bug?
Then it, you know, so if you have it enabled, if you don't use inbounds, it'll come out with a nice error message that says, on this line, you've got a problem. If you don't do this, it might like hang or crash your system or just completely exit without an informed of error message.
It will probably set fault.
It's
I think limited inbounds in the loop is a nice design because if you put it outside later, you change your code, you know, you didn't realize, you know, that, you know, you have inbounds outside, right? Then it doesn't check the bound. The, you know, the code may, you know, produce errors or wrong results. So put, you know, the line where, you know, then should be, you know, it's, you know, make sure that it's inbound. You know, I think it's, I like it, putting inbounds inside a loop.
I think it's far too tempting for smart over optimizer types to put it in there when they really should leave this stuff out. But yeah, interesting.
It's only meant if to be used if you know for sure that you've got your system tests and you're absolutely sure about this. And then yeah. Go ahead, Bill.
It's so funny because just before you said that, Eric, I was thinking like, well, what I would do is I would put it in just a few places incrementally. And then you said smart over optimizer type. And I was like, okay, he's talking about me. And I know I would get myself in trouble doing it. So.
Bill?
Yeah, Ben, regarding the benchmarking, I noticed that there's allocations, 62 allocations there, and I guess that's the size of the data that was allocated for your initial attempt. And then when you went and started using loop factorization, allocations went down to 0. Is that just the way that could you explain that more?
Yeah, I actually didn't notice that in preparing for this talk.
Is that because of the buffer, like the vector buffer that you did and the other one is not using that?
Certainly, that's right. This fill here is allocating. And the question is, but is that really allocating 6 kilobytes? That seems kind of like a lot.
And why is the other one, what's it, it's interesting to me that it doesn't do any of that on when you use the package, the loop factorization package.
Yeah, I think Mark has used loop factorization a lot more than I have. Mark, do you have any insight here?
Yeah, I think the loop factorization threads are actually much lighter weight than the full bound threads. So I think if you wanted to lower the code or something, then kind of show the difference. But yeah, I think the loop vectorization kind of just takes advantage of knowing the full loop structure. It doesn't have as many whistles as threads, so it's not as general. But basically, what these macros are doing, these things with the @ symbols, they're essentially rewriting the code. They basically, what macros do is they take a code and output different code. And so essentially what Chris Elrod is doing here with loop vectorization is just changing this and putting in both ABS instructions and also kind of inlining threads. By the way, he works for Julia Computing now.
Yeah, I knew that. Yeah, I was going to mention that he did such a great job with loop vectorization that he quit his pharma job and he now works for Julia Computing. Yeah,
It's
and I didn't,
yeah,
I failed to mention that this ampersand symbol here in front of a string is Julia's syntax for a macro. And what macros do is they input then this code block, and then they output another code block into that same section of your code, which kind of transforms it to do whatever you happen to do. And so in this case, threads at threads will just take this for loop and do that partitioning. And it spawn processes on different threads and stuff, all kind of in line there.
So far, we've mostly had questions from SciComp members about more computer sciencey flavored aspects of this. Are there any questions from SciComp members or non-SciComp members that are more about like the basics of Julia, the logistics of Julia, like how to get it installed, or a syntax question or anything like that? Like I was just gonna even ask, maybe this is unnecessary, but I was just gonna ask a few questions about comparing the syntax to Python, which I'm more familiar with. So it looks like, in Python, when you define a function, you say def function name arguments. Here it's function name arguments. And then you pointed out the macro, which is kind of similar to a function decorator in Python, I guess. It's nice it's the same symbol and it kind of has a similar thing, but it seems like the macro is more particular or more flexible than function decorators in Python. But are there any questions about that sort of thing, more like introductory aspects of the material?
I have a question. I was wondering about like, function and package discovery. So one of the nice thing about MATLAB is that all the functions are there. If not, you need to buy them. But it would tell you, oh, you don't have that toolbox, come pay me more money. Whereas in Python, it's you need to know that the function that you need is in scikit image. When people start learning Python like me, it's actually really difficult to figure out where I should be looking for help, because there might be a whole package I'm missing. How do you think that compares with Julia and kind of package discovery and function discovery?
There's a juliapackages.com, which keeps track of all packages, and you can kind of search for various keywords that'll go through the documentation and the readmes of these guys to kind of look for the package that you need. There's also discourse.julialang.org, which is just a news group essentially. It's kind of the go-to place for people to kind of ask questions and get help for Julia. Julia, also the way you get help on a function is with the, you just hit the question mark, and so you can do a help on, say, print, right? And it'll kind of give you inside the REPL kind of the doc strings for whatever function that you happen to choose. There's actually another function called apropos where you can search for a string, right? And it'll kind of search through all the doc strings and the function names and kind of give you a list of everything that has that string in it. So that's kind of another way to kind of discover where things are. In terms of installing packages, you just have to say, well, first you can go into package mode by hitting the square bracket, and then you can hit status or just ST to see which packages you have installed. And so you can see I've got installed these couple dozen different packages. And if you need to add a new one, you can just say add, I don't know, Optim for the optimization package, for example. And it'll go down, it'll go to the kind of the general repository, which is hosted by Julia Computing. And that's kind of the main one, unless you have your own kind of registry for packages kind of within your institution. This kind of is generally where everything is. And it'll kind of download and install that for you. And it does, the Julia Package Manager is kind of very similar to Conda in that it uses semantic versioning. And it makes sure that all the dependencies are compatible. So when somebody publishes a package, they have a list of dependencies and what version of those dependencies are needed. And then PKG, the Julia Package Manager, just like Conda, will go and make sure that you've got a consistent set of packages across all the whole board. Did I answer your question, Mark? Can you think of anything else to elaborate on there?
Yeah, I would probably recommend juliahub.com over Julia Packages. I think Julia Hub is run by Julia Computing. It also searches their, so there's that search thing up there. You can just type in print. And I think it also searches their kind of cloud platform. So
There we go.
It would be cool for a future meeting to do like a packages rundown for a couple different languages. Have, like Java, C++, Julia, Python, like one person from each, 15 minutes, and just say like, here's my favorite 10 packages and one function from each package.
Hey, Ben, I had a quick question too. Could you go over how you manage different versions of Julia? I see you're using 1.7. Like on my machine, I'm at like 1.5, another one at 1.6. How do I go about getting to the latest version without wiping the old one completely? Is there a way to do that seamlessly?
Wiping the old one completely. Oh, well, like I said, what I usually do is I just go to julialang.org and I download a new version. And then what that does is it puts me into, I've got, hold on here. I've got, if you look at my Finder on my Mac, I've got Julia, 3 different versions of Julia on it, right? And they just sit side by side on the same machine. And if I want to pull up, I've got aliased as Julia 1.6, right? That, and I can pull up Julia 1.6 if I want instead. Oh, but hold on. Oh, this is because this is not my Mac. Julia 1.6.
and there's
And there it is. And then there's a separate environment for that versus Julia 1.7, which has its own separate environment. Right, you can see the list of packages I've got installed on 1.7 is different than the list of packages on 1.6. So you got separate environments for the two. And I actually didn't go into that, but you can activate my demo environment, right? And now this string over here indicates, what environments you're in, and I can do a status here, and you can see it's completely blank. And from there, I can then start adding whatever packages and create your own environment. Python has a similar mechanism as well, right? And
Ben,
yeah.
so the Julia up thing, it's actually solves that problem directly. It's a version multiplexer for Julia.
I didn't catch any of that. Say it again.
Julia up. So I just put the link in the chat there.
Oh yeah, yeah. Mark was mentioning this to me yesterday.
And on Windows, actually, if you install Julia from the Windows Store, it will actually install Julia up for you.
There we
go. But basically, that will let you switch between versions and also make sure you have the latest version of Julia.
So if I do Julia up, do my packages port over, or do I have to reinstall the packages?
That's actually fairly easy to do. You can say if you switch to if you activate a different environment, then you can just say instantiate, and it will download everything for the current project if they're not already there.
Yeah, I think that's a key. You need to create a different environment. So the default environment is, as you can see, this version 1.7. So it's a version specific environment. Whereas these other environments can be shared between versions. And so the key is just to create a project specific environment. And then you can load that from different versions.
Yeah.
Thank you.
I would agree. That's the way to do it. Yeah, you want each of your projects to have its own environment. And then from there, it's easy to switch versions.
Hi, Ben.
Yeah, Tim.
So yeah, you mentioned there are several ways to install Julia on Mac. Which one would you recommend? Or
like I said, I'm old school. I've been using Julia since version 0.3 since 2013. And back in those days, your only option was really to go to julialang.org and kind of download manually. But these days, there's all sorts of different ways. You can do homebrew, or you can use Conda, or like Mark said, you can use Julia Up. Where did that go? Julia Up. I've never really used any of the other ways, so I'm not the right person to ask which way to recommend. I just do it the one way that I do it, and it works just fine. So
I think on Mac, I would the other thing you could do is the homebrew cask.
Homebrew.
That not just the there's two different things with homebrew, I forget, but the cask is better than the other one. The difference is that I think there's like a self-built version of Julia by homebrew, where basically it's building it from source. Whereas there's also kind of the official Julia binaries. And so the cask gets you the official Julia binaries. The problem with the version built from source is that they tend to let the dependencies float a little bit more. And then they don't run like as comprehensive tests, so it might not work. This is the same issue that we have on CondaForge. And I'm the one running it at the moment. So, but I've been kind of fighting to increase testing and trying to pin the dependencies down a little bit more so that you don't end up installing a set of packages and dependencies that are inconsistent.
So if you install Julia through Conda, do you update the packages through Conda as well?
You can. I would not recommend migrating Julia versions within a Conda environment. I would start a new one.
Yeah, but once you start a new environment, but when you like want to download the packages or update the packages, like so you can build use Conda to update the packages, or you just use Julia package management.
Oh, I see what you mean. I mean, I think it depends on the package. There's somewhat of a hybrid. So there's not too many pure Julia packages that you can install via CondaForge at the moment, although I think people are starting to work on that now that Julia is available on CondaForge.
Yeah, because for Python, if you install through Conda, it's better to update the packages through Conda. Otherwise, sometimes the dependency might be messed up.
Right. I think there's another issue of like shared libraries. There's like a differential equation solver called sundials, for example, that you can both get through Julia's package system and through CondaForge, and there's some issues with trying to go between them, but we're trying to smooth those over.
So I think there's only 15 minutes left, Greg. We should probably switch to you, right? I'm happy to.
Yeah, that's true. But I really also want to get to
offline.
Ruchij's question as well.
Yeah.
There's another hand up. Let's do that one last question, and then we'll do the final presentation.
Okay, yeah. So I have a quick. It's a computer science question. So, does Julia scale according to hardware? So is it like if you have better hardware, you would get better speed up, or is it more like a smart compiler optimizations? What actually is responsible for the speed up?
Well, everything. I mean, it happens at all levels. I mean, Julia uses LLVM to generate all its machine code, and I think so. Its single-threaded compiler, I think, is really good. If you're talking specifically about a for loop, that's compiled. It's not interpreted like in other languages. But Julia also has kind of from the very beginning, they were very much concerned about scaling up to multiple cores and distributed, and so it's got very good support for distributed processes and threads within the same machine as well. So
you want to show code native, or
I'm not sure we have time. I want to make sure we leave room for Greg's talk, right? We don't need to dominate the discussion here, but Richard, I'm happy to we can talk later if you want.
Yep, sure, that helps.